Yeah, homework 8, it's the worksheet. It's right here. Packet, okay, whatever. Alright, let's review everything we've learned. Yay!
Yeah!
Hold on tight. Okay. Alright, so we ended with this example of getting a Frosty at this strange restaurant, and then we gave the definition of conditional probability. We said the probability of B given A is equal to the probability of A intersect B over the probability of A. At this point, I hope this formula is becoming intuitive. It's not a formula necessarily that you're thinking you need to memorize per se. It should just kind of make sense geometrically, even if we're thinking about Venn diagrams. Now, in this example and the example we gave yesterday, it kind of was football over volleyball. But just to be clear, it could be all sorts of other different shape regions. You know, it could be that we're looking at like the crescent-shaped area. It happens to be the intersection or something. It could do all sorts of things. Whatever. The point is, probably that both occur over the probability of the condition that we're putting on the situation. I picked a volleyball because volleyball is the best sport that involves round objects.
What about juggling?
Well, okay, no, I might say juggling, but then you get into this whole debate that about whether juggling is sport.
What about juggling on a unicycle?
Or math.
That doesn't involve
Do you not remember when we did angular and linear velocity with the wheel?
No, I'd rather.
You can juggle with volleyballs too.
Oh. You can juggle a unicycle with it.
All right, the truth that we expressed and trained ourselves to express on the warm-up today is now finally on the board here. There it is. We've said it many times over the last day or so, but certainly that's the case. It's also equivalent to say the other way, or actually one more way, which is a little harder to see that it's equivalent, but someone can maybe just prove quickly why this is also true. This looks just as the multiplication rule. You like move it around or something. Yeah. If these are intersection, the A and B.
Is that like the stuff that's like in the middle?
Yeah, there's the stuff in the middle. Yeah. So the probability of A times the probability of B equals the probability of the intersection is actually a test for independence too. And the way that you can see that is that we've been talking here about the probability of A is equal to, what is the probability of A given B? Oh yeah, that's the probability of A intersect B over the probability of B. Isn't that what this equation says?
yes.
Okay, well then, I rest my case. Okay, multiply both sides by PB and you got it. So, and I want to make a point here that if, we said this earlier, if two events are independent, then you can multiply their probabilities to get the joint probability. Yay. But what we're saying now is that test, the converse works too. If the multiplication principle works for two events, it must be the case that they're independent. It actually works both ways in terms of logic. Right? So we're inviting you to use that piece of logic here now. So that's a perfectly way to have justified, if you want, to have justified the last example of the warm-up today, the last part of the warm-up. You could have said, well, the probability of, if I multiply the probabilities, I don't get the probability of the intersection. Therefore, I rest my case. They're not independent. That would be a fine thing to say too. Okay. Cookies. Jars. Let's do it. Imagine you have two identical cookie jars with no markings on the outside, with a very small opening that you can't see inside either. Okay, so it's a dark room. You have no, right, okay, you're just reaching into one of these two jars. And by the way, every time you've tried this in the past, someone has mixed them up afterwards, so you don't have any idea. We laid the groundwork for this, and there are cookies inside here. It's extremely likely that this would be the case. Okay. So I'm going to organize this using a tree because, that's one of our favorite tools. We've been using that recently. We got jar A, jar B, and because of the circumstances I've described, the probability of getting jar A or jar B, have you gotten the picture, is 1/2 and 1/2. Yeah, good. I'm trying to paint the picture that they're equally likely. All right, so jar A, if we're inside jar A, what are the options? Chocolate chip cookie, and the same options, I guess, or a peanut butter cookie. Ooh, yum. Okay. Tough choice. They both sound really good to me. Okay. I think I'd be happy with whatever outcome. 5. What? Fill in the probabilities here for me. 3. 3. Yeah, 1/3 if you're 2/6, whatever, and 4/6, however you want to write it. Okay. Good. We've done this before. So not super exciting. Let's also compute the probability of all the joint probabilities now, right? The probability of being in jar A and getting a chocolate chip cookie is equal to, you've said it before, but it's just 1/2 times 3/5, right? And what does that come out to be? Now the thing we haven't been able to do until just now is to actually say what we've just done. That's the probability of jar A times what? The probability of... Yeah, it's actually, the reason we haven't said this yet, early on the first day we were drawing trees, but no one stopped to say this because technically this is not the probability of a chocolate chip cookie. It's the probability of a chocolate chip cookie given that you're in jar A, right? All right, so, and just so you know, I think this should look familiar to you. This is also still just this rule for conditional probability if you divide by the probability of A or something, right? Anyway. So I don't know that we need to write that out each time, but I just want to make sure you understand that like all the symbols and all the mathematics that we've been talking about, it all works. All right, if you're, what about this joint probability that you're in jar A and you get a peanut butter cookie? That's of course, let's actually just say 2/10 maybe. I'd like to let's keep the denominators the same there. And jar B and chocolate chip cookie. Come on, just out of respect, man. Come on, seriously. Don't make me come over there. Okay. What is that? 1/6. Are you multiplying with me? Everyone having fun? 1/6. Okay. And down here? Hopefully it's 5/6. No, did I multiply wrong?
Right, yeah, you're right. It's 1/3.
This was supposed to be... Yeah, this one here. What is that? 2, yeah, 1, well, okay, or 2/6. Oh yeah, we're okay, yeah, 2/6. Yeah, so hopefully these add up to 1/2 and these add up to 1/2, so we're good. And they do. These add up to 1/2, these add up to 1/2. The whole distribution, it adds up to 1, of course. So we're good. What was the question? We didn't even ask the question yet. What's the probability of picking a chocolate chip cookie? So now, unconditioned, we want the probability of a chocolate chip cookie. How do we get it? Of course we've done this maybe before, but we just need to add up 2 appropriate things here. Right? But let's and I think it's good to kind of lay the symbols on top of this though too to understand like the form of what we've done. That's the probability of A and chocolate chip cookie plus the probability of B and chocolate chip cookie, right? And in fact, in some ways, sometimes this is called the law of total probability. Like if you add up an event and its intersection with every other possible event, then you've got the total probability, right? So it's sometimes called the law of total probability because you're adding up over all the outcomes. You could say A and chocolate chip cookie, and over here you could say not A and chocolate chip cookie, right? We got it all. We've got all the possible outcomes that would amount to just getting the chocolate chip cookies. So, okay, now here comes the hard part, fractions. Did anyone add those yet together yet for me? 7/15. Can someone just check your arithmetic there on that? 2 7/15.
Yes, she's correct.
You're just going to trust her like that?
No, it's,
All right.
it's funny.
I have a follow-up question, though, and that's this. Assuming that you have a chocolate chip cookie, what's the probability it came from jar A? That is, I see you coming out of the kitchen with a chocolate chip cookie in your hand. What is the probability that it came from jar A? That's a different conditional probability than was given in the question. The conditional probability that was given in the question was that, which is very simple, just was given in the question, is what's the probability that you get a chocolate chip cookie given that you're in jar A? But this is flipping that, right? This is what's the probability that you're in that you got it from jar A, given that you're holding a chocolate chip cookie, right? That's a different probability. It's a very different answer that we get. how do we get that? It's the probability of, let's reconstruct this. A intersect, what are all the pieces we need over the probability of the chocolate chip cookie in general. So the intersection we calculated is one of the things we calculated. It was the top branch on the previous picture. Yeah, 3/10. Right, that top branch. And the total probability of a chocolate chip cookie, we added up. That was like the point of the previous slide, in fact, was whatever Katie said, 7/15. Okay, we're trusting here still, I guess. Okay. Okay. So now we have to do fraction work. You have this one ready for us, Katie? You say one more. What was it?
Well, I'm sure like 9/45.
9/14? Yeah, you do the fraction work, you'll see. But honestly, if we had just given you the original problem without any of the tree or anything and just said, ready, do this, you would have been like, whoa, that's actually it. Doing the chocolate chip cookie is actually a little bit of work. I mean, if you write out this calculation, let's see if I can do it. It was 3/5 times 1/2 over 3/5 times 1/2 plus times 1/2. 1/3? Is that what it was? Yeah, that's where this all came from, right? If you really wanted to go back on it. Let's see a hand somewhere. Okay. Okay. Oh, you're good now. Anyone else want to say something about cookies and jars? All right.
Can you have a cookie party like you did on High Day?
If you bring cookies on any given day, Isai, we will help you eat them.
All right.
All fun.
Tomorrow is great for me. What about you guys? Great. Yeah, I thought so too. Yeah. All right, so here's a statement that I'd like us to just kind of prove visually quickly. You could have a more rigorous proof, but that is the probability of A or B occurring is the probability of A plus the probability of B minus their intersection. I want you to draw this with a Venn diagram and think about why the area of that MasterCard region is given by this expression. That is this region right here. Like, why is that given by this formula? Everyone turn to your neighbor and explain.
I have no idea.
Why did the direction of the loop change shape?
Because one of them is and one of them is. This is disgusting.
The first one makes
If you know they're independent, then you can multiply. You get that. But if they're not independent, then it needs to be given, like was in the warm-up today. I gave you all three things. All right, did you prove it to yourself? Yeah, I mean, we got this like double counting issue, right? You counted the overlapping area twice. Okay, so just subtract one copy and we're good again, right? This is the way to say it, maybe. All right, what's the probability of jar? Actually, I think I gave you almost identical problem in your first day of warm-up when we did probabilities. I asked you, what do you know so far? Okay, so this is a problem I already know you know how to solve, but let's try and frame it in terms of this formula to make sure this is saying what we wanted it to say in terms of this problem that we've done before. So we're asking, what's the probability of getting a jack or a heart? So that's the probability of getting a jack, which is
Jack's the number, okay.
the probability of getting a heart, which is what are each of these things? Jack is what? Yeah, 4 out of 52. Heart is 13 out of 52. We're not going to reduce because it's actually a not doing us a favor here. And then the probability, wait, is there such a thing as a thing that's a jack and a heart?
Yes.
Oh, there is? There's exactly how many of those? All right, well, so this is a little overkill for this problem, but do you agree that this does conceptually give us, and computationally and conceptually make sense of this formula? Hopefully it works here.
Mr. Chase, I like this.
Thanks for that vote of affirmation. Okay. Now, one thing that's a little bit tricky about this sometimes is when someone says or, in the English language, there's some ambiguity, isn't there? I mean, we aren't very disciplined in our language, which is why mathematicians always have to hijack English words and make them more precise, right? So we're just always going to agree that or, in our case, always means the inclusive or. That is, includes the probability of the overlapping event, right? So that is, it includes the possibility that we get a jack and a heart, that one card, for example. Now, in English, just to prove the point here, if someone comes up to you and asks you after dinner, would you like tea or coffee, which kind of or do you think they mean? They mean the exclusive or, please don't say both, right? They probably don't mean both, right? They say, would you like tea or coffee? And then in the very next sentence, they say, would you like cream or sugar? What kind of or did they just use in the next sentence? They use the inclusive or, because they're welcoming the choice of having both. Right, in the very next sentence. So you can see that we're very duplicitous as English speakers. So but in English, as mathematicians, we need to bolt things down a little more, right? So as a mathematical community, we'll just agree that by or we always mean the inclusive or. So when your dad or mom approaches you someday and says, hey, we have enough money to give you a brand new car or pay for your college education, which would you like? And you can say, yes, please, both. I learned in math class, Mr. Chase told me that by or you mean one or the other or both. Okay. Yes.
Is there a different way to phrase an exclusive or?
One or the other, but not both, is what you have to say in English. And lawyers, of course, make their business. They always have to say and or, and stuff. They always are very careful to say this kind of stuff, right? English is so messy. Math is beautiful. All right. Maybe we should all lobby to include now into the English language the word XOR, right? Which is the word that computer scientists or mathematicians sometimes use to talk about the exclusive or. The XOR.
Oh, yeah.
I don't know. You started. All right. With that layer of interpretation on this problem, try this while I pass out your homework. It's not meant to be computationally very intense. Go for it. Enough for my super. Wait, no. No. Sorry. Sorry. Dude, we just did homework 8, sorry.
Okay, yeah. I was looking at the homework.
No, we did homework 7 for homework.
Also, it's right in front of me right here, but maybe I was looking at that one. And this was upside down. Haha!
What do you do? Okay,
Wow, this is so much fun. I know.
right.
Oh, that's
I mean, you're right now, right? So.
you're so funny.
I am. Mr. Chase, we have an extra.
Oh, I did just. Here you go.
What's 65 plus 20?
It's 85. Are you kidding me?
It's 40.
So, yeah, like I said, computationally there's not much to do, but we just want to make sure that as we interpret this, we want to think, okay, this 30 is included in the first two, right? I mean, there's overlap here. I want to make sure you're clear. The way the survey went, we'll say, is that like someone asked, like, hey, did you donate food? And the people in this category did say yes, right? They did check that box. Yes, I did donate food. So this is accurate. We just want to make sure we understand that, again, the reason that there's like a little bit of suspicion on how to interpret this question is because English is messy, and so we'll just, but we had this conversation already, so let's move on. So what is it? 65 plus 50? Minus 30 over 200. We can just share the denominator instead of having to write it 3 times. And we get something. What is that, 85? Over 200? It says a percentage, so let's report it that way. What is that, 42.5%? Good, wonderful. So yeah, we got some people, we want to get it capture in our news article we're writing or something, we want to capture some sense that people are generous. And look at that, 42.5% of people did something. That was great. Good job, people. I should also, no, everything's made up. Okay, always. All right.
Wait, just like the pictures you put in at the beginning of the unit?
Oh no, those are real. Let me say one other thing. Okay, so now, is it ever possible that when we're doing this calculation, the probability of A or B occurring, that they probably could just be computed as probability of A plus the probability of B, and you don't have to worry about the intersection? If and when is that okay? Did you almost say the word independent? Don't say the word independent, because independent events can happen simultaneously. Yes, the word is mutually exclusive events, right? So what's an example of even a problem we've done in the last couple of days you could use if you like? Something. Okay, yeah. What's the... Yeah, turn left and turn right. Okay, huh? Yeah, getting heads or tails. What's the probability of getting heads? Well, that fills up the probability space, but you can't possibly get both. Those are mutually exclusive, right? What about getting a sum of 6 or 9 on dice? They're mutually exclusive, right? You can't both get a sum of 6 and 9. So you're safe to just add the probabilities. You don't, or I guess we could also say you are subtracting the intersection. It's just of size 0, right? So it always works. It's just sometimes there is no intersection. What about either die shows a 2? The first one could show a 2, so there's a probability. The second one could show a 2, compute that probability. But then could they both be 2? Yeah, so subtract the intersection probability. Do you see how this works? Not all of the problems on this worksheet deal with this. I'll just warn you, there are many that you might need this tool. I know the title is this, but whatever. It's just mainly practice on all the stuff we've been talking about. Also, one other disclaimer, if you're not in AP SAT, please skip number 4. For now. Okay. If you're good.
I did it, but I didn't do the right thing.
Yeah, you can just skip number 4. I'm not sure why it appears in the standout. Just you can cross out number 4. If you are in AP SAT, you can try it though if you like. And all of us will be able to do it on Monday when I cover that lesson, but I don't know why it appears on Monday. There's no reason that anyone can't try it. I don't know. All right, do your work.